Hi everyone, my name is Rojas. It is a joint work with PhD Andreas Gribonk, and it is titled Target-Oriented Average Search Trajectory in its Applications to Artificial Neural Networks. So, I'm going to present the usual model of artificial neural networks, the optimization task and learning algorithms related to the problem of minimization of this model, and the optimizer's house of horrors that comes from the model that we want to minimize. Then I will present what is a global optimization problem, and then our formulation of this novel trajectory to reach certain global minimum, and some approximations that we do to approximate the prediction function, and this algorithm we call it cycle, that is related to the Abs linear form and the global optimization. Some results and comparisons and some conclusions. Okay, so as we know, the artificial neural network model is the average of the errors between the loss function in the whole training data. So our training data is referred to xk and yk. The variables of this model are the weights and the shifts, as you know, that is represented with w. And the function that represents the neural network model, these compositions between the hidden layers, and the activation function is f. And that's all. That's our objective function of our minimization problem. So the most used learning algorithms to solve this problem is steepest descent direction, that use the usual technique of backpropagation. And then the variance of certain momentum methods, that is a linear combination of the steepest descent direction and the last function value, and the stochastic gradient method, that all we know that is pretty useful, but the most important thing is the step size. So from our experience, the step size, it can be 1 over the square root of the iterate count. Okay, so in order to solve this problem, we can see an example. So a single layer case with constant output weighting, and the hinge activation function, that is as known as the rectifier linear unit, can be mathematically described as f. Here we can see that the hinge function is non-smooth in the kinks of these branches, but it's remarkable to know that the minimal values of this composition occurs in that kink where the function is not smooth. Okay. Also, this function is multimodal because it has higher values that are local minima than the global one. And it also has a plateau that sometimes it refers when the function surface is constant, and it occurs because the weight n+1 that we refer to the shift or bias is larger negative, so the hinge function turns to 0. If it is negative, the maximum between 0 and something negative is 0. So the gradient will vanish identically on the shifts and weights, and also with respect to the inputs. Okay. So there is a graph, an example, that with two variable weights. So we just consider a neural network with 2 weights, and then we can see that there are a lot of kinks of this surface, and so far we can argue that the global minimum of this function can be here. Okay, I will explain with more detail afterwards. And so this is the contour of this surface, and as we can see, there is the plateau where all these points that makes the plateau are local minimum, and so the usual optimizers like stochastic gradient method and steepest descent could get stuck there. Okay, so it is a problem because we are not minimizing globally the function. So what is a global optimization problem? And in this case, it's usually non-smooth because all machine learning models are non-smooth. So most of the optimization methods go downhill, but they don't have the capacity to go uphill since it gets stuck in the local minimum. And so it gets stuck possibly in also saddle points because the gradient turns equal to 0. And to find out what are the lowest value of the function between this whole set of local minima is pretty difficult. So there are two paradigms or two techniques in principle. One of them is space covering, that is kind of deterministic because it looks in the whole domain of the objective function where is the minimum. But talking computationally, this is pretty costly because it exceeded the computational limitation, and so also the difficulty is because the density of the domain. The other techniques are non-rigorous. That is that it uses some stochastic and statistic functions in order to search the minima. And the other is deterministic but heuristic searches. That is that the trajectory is calculated by a deterministic model, like an equation. But heuristic is called because there are dependent by some parameters that the user select, and some hybrid methods. It is remarkable that we are in this section. So our method is deterministic, but with two heuristic parameters. Okay. So this is our way to calculate the search trajectory. This is an ODE. That the idea is that the current search direction x of t, the first derivative of this solution goes towards the steepest descent direction. The closer the current function value is in this trajectory is to the target level, and the more rapidly the direction is adjusted. In the limit, when the function value at this trajectory tends to c, the trajectory reduces to steepest descent. Okay, so here C is our target level that we want to reach. So our solution of this ODE makes that the function reduces to this C level. That is our target level. It has the capacity to go there if the C level is not too ambitious. For example, any machine learning problem has the lowest C can be 0 because it uses always the norm of the error. Can be the L1 norm, L2 norm, or L infinity norm. So all of them are graded down or equal to 0. And in homogeneous objectives, that is that the function value is proportional from the distance of the development point. The local minimizers below C are accepted, and if it is higher of this target level, they are passed by. So they are not considered. Okay. So many as I told you, all the models of machine learning are piecewise smooth. So these functions can be approximated by a piecewise linear model that has some quadratic error that we call this term. So the difference between the piecewise smooth model and the piecewise linear model is bounded by this quadratic term. So if we, in each piece, we can represent in each piece the piecewise linear model like in this form, because it is linear. Okay, so in each piece we calculate our search trajectory with our magic ODE that has that it was the master thesis of Andreas, and then we get that the solution is a circle. Okay. So if we evaluate the function in this circle, we get that our function has a trigonometric form, where omega is 1 over this omega is the radius of this circle, and the initial curvature is given by the ODE. Okay. Okay, so every function that is piecewise smooth and is composed by smooth elemental functions and piecewise linear functions like absolute value, the mean function, or the max function like the hinge function, can be approximated by a piecewise linear model in a reference point. Okay. So as I told you, the discrepancy between the actual model and the piecewise linear model is bounded by this quadratic term. Okay, so that is an observation theorem. The other thing is that any piecewise linear model can be represented in the abs linear form. So the abs linear form suggests that each non-smooth okay. Each piece of the function where it is smooth can be represented by a set variable, and replacing this set formulation in the actual piecewise linear model, we get the abs linear form. That is suitable because can be computed automatically by algorithmic differentiation, and in order to make a code, it is useful because we can go in each polyhedra or in each piece where the function is smooth, that in each one of these polyhedra are defined by a signature function that depends on this set function. Okay? So, our algorithm is the following. We have our prediction model that is phi, and then we make a piecewise linear model, piecewise linearization of it. Then this piecewise linear model is referenced by an arbitrary point of the domain of our prediction model. Then we select arbitrarily, but arbitrarily. It's me or down both? Okay. Like this. Hola, ¿me escucha? Sí. Okay. Okay. So then, so we select the initial tangent arbitrarily, but that the norm of this tangent is 1, and compute the signature vector over the reference point that where we are doing our piecewise linearization of our model. Then compute and follow the circular segment obtained of our ODE. Determine the minimal time that this trajectory takes to the boundary of the polyhedra that we are, or if the target level is inside of this polyhedra. In the last two steps is that if the function value is less than or equal to the target level, we have three possibilities. we lower the target level in order that our search direction is still looking at another lower target level, that if it is not too ambitious, it can be done, or go to step 1 with the reference point equal to the point where is the boundary of the polyhedra, or terminate if the user think that is good enough our minimal value that the algorithm found. Else, if the function value doesn't hold this inequality, that is that the function value is still higher than the target level, then we set our iterate in the point of the boundary of this polyhedra, and go to the step 3. Okay, and making again these circles. So there is an example, and pay attention to this because it's very important. It is how it works, our algorithm. So if you remember, I showed this graph of the loss of the empirical risk surface of our function. So this is the empirical risk surface with two variable weights. Okay, so we start in whatever we want, but in this case we start here. So we set our target level equal to the half of the empirical risk error, the initially empirical risk error. So it's like a contour that gets in here, okay? The first target level. So far we reach this target level at this point. Okay, but there is an observation. We didn't make the circles since by lack of time, but imagine that there are circles here. So there are circles interconnected these points. So these points are the values that is calculated by calculating our algorithm. So it goes by circles through each value until it reach actually a minimum that is pretty near to the global minimum. The global minimum is here. Okay. So it is, but however, it doesn't reach this global minimum, since the target level that it was calculated at first, it was too ambitious, because our strategy is to halve the target level that it was reached in order to create the new target. So the new target here is lower enough of the minimum value that has this surface. However, we can see the capacity of our trajectory to go downhill. It goes downhill until here, and it has capacity to go uphill in order to look if it can find another lower minima than this one. Okay, so it is pretty important. Again, we see the plateau. We don't get stuck in the plateau as a stochastic gradient method does, or a gradient descent method does. Okay, so it's pretty curious how our trajectory has the capacity to go to search a global minimum. Okay, so another more sophisticated example is the Griffin function. To approximate the Griffin function with a neural network. Here we present a neural network with 10 intermediate nodes. And since it is a 2D example, we have 20 weights in this neural network of only one layer, and 10 biases or shifts. Okay? And we do the training of this neural network with 20 points. Okay? So what we can see in this figure, the stochastic gradient method, it gets oscillations after 10,000 of iterations. It gets oscillated between the kinks that I presented before, but more sophisticated, because we are treating now with 20 weights and 10 biases. That is our independent variables of our neural network model. So the reach minimum that the stochastic gradient method arrives after 10,000 of iterations is 0.07. Remember this number. Then we present gradient descent. Gradient descent goes lower, but it has the same problem. Sometimes it is called the zigzagging problem, because at these functions that are non-smooth, when it tries to arrive to the minimum, it starts zigzagging in this valley, but it is valley that is like a kink. It's a kink. Okay, so the gradient descent method after 1,000 of iteration is like around 0.054. Okay, but our method can really approximate the Gribon function, and we can see the oscillations of the Gribon function in this plot. So we start with the target level, and that is this line. Then we halve it because we reach it. Actually, we halve it, and we get again to this new target level that is the half of the first one. Then, after some iterations, we go downhill and uphill in order to reach the new target level that is the half of the last one. And then we halve it again, but it is too ambitious now. But however, the method in the algorithm can go downhill and uphill in order to try to reach this new target level, where we think that the minimum is. The minimum is. Okay? In doing this process, we actually get a lower minimum that a stochastic gradient method and gradient descent method don't reach. Okay? Because we reach after 1,000 of iteration, well, actually we reach the minimum, the lower minimum than SGD or GD, 0.03. So it is the lowest of the three studied. Okay, and we can see that the last target level was 0.31. It was too ambitious, but our trajectory gets a better result than SGD or GD. So the remaining task of our algorithm is that we can refine this targeting strategy. We can do a different strategy of targeting. Instead of halving the target level of the initial empirical risk, we can do another thing. And that's the first point. Then we can extend our algorithm that is made in C language to extend to the deep learning, because we are treating just one layer. But the whole analysis, the mathematical analysis, is already done for an arbitrary number of layers, and the algorithm is already implemented in a pseudocode. Okay, so the whole theory is already done. So we just have to do the programming. Then the third point is application to a standard problem. For example, the MNIST. No, that is approximate certain numbers that anyone draw, and say, in passing through our neural network, say if it is an 8, 9, or whatever number that we have drawn. The fourth point is the matrix-based implementation of this neural network, because we know that in each layer we do linear transformation, affine transformations of the input data, and go as many compositions we have, as many layers we have in our neural network through the high performance computing code. The fifth is the exploitation of the low rank updates in polyhedral transitions. We say that it's low rank because there is just one change of sign between when we search in one polyhedra to the other polyhedra. There is one change of sign of this signature vector that defines the polyhedra of each piece of our piecewise smooth function. And the last one is sample-wise version, like that's the stochastic gradient method. And so that's the reference, and thank you.
Gracias. Are there any questions or remarks? moments?
Sure.
I don't know if it's a good question, but what happens if you never get a minimum?
Please
You
repeat
never
the
get
question.
the lowest value.
Okay. The question is that what happens if we don't arrive to the lowest value?
The target level.
You are saying the global minimum or the target level? That
The global minimum.
the global minimum. Well, it depends on how is the strategy of setting this target level, because as we saw, let me show you the slide here. As we saw, we don't reach the global minimum because we were too ambitious, or our strategy for causality doesn't make that our trajectory gets exactly to the global minimum. But here is the global minimum, and we reach in the neighborhood. So it's a strategy that makes this difficulty in order to reach the global minimum. But it's better than stochastic gradient or gradient descent, because as we start here, it will get stuck in here in this plateau, because here are local minimizers in the whole plateau. So it's actually an improvement. Another question?
There is no proof of anything. As we said at the beginning, if you don't cover the whole space, an algorithm that does finitely many evaluation goes somewhere. Afterwards, you can deep a mile deep hole somewhere in the neighborhood where the function wasn't evaluated, and obviously you miss the global minimum. So it is a heuristic strategy.
But it's better than the actual optimizers. Another question?
Okay, if there are no more questions, then we thank Angel again. And we continue with the talk by Hernández.
Well, my name is Alejandro said, and call me Alex. I'm going to talk about a system created with ultra-cold neutral atoms, and we will put it in an optical square lattice. So here we have the Bose-Hubbard Hamiltonian, which is the model of the situation, where we have the kinetical term here that is composed about just a jump in the lattice. We annihilate one particle in the J side and we create other in the I side. It's over the nearest neighbors, and we consider the Hermitian complex too. The other term is the interaction term, and it only comes when two particles are in the same side in the lattice. Of course, U and T are positive real numbers, and well, this Hamiltonian is obtained from the many-body system Hamiltonian that is more complex. But we choose these quantum fields, something like localization, creation and annihilation operators, like A. And it's a strange combination of it. But I will not say the details, it's not the purpose. But we have to have in mind two keys. When we consider fermions in the lattice, well, this term will be 1 or 0, the interaction term, So it will be zero anyway. Doesn't matter what's the value of u. So it doesn't matter, just the kinetic term. And if we consider bosons, then we will have interaction whenever we have two or more bosons in one side. So this will create a gap. When we have more than one boson in one side, there will be a gap, and also an energy cost for these states, because we are adding energy, because u is a positive number. So, well, we will contemplate another model that is an electron in a 2D lattice. For it, we have the block energy function for the type binding, that is this on the left, and we will apply here the pile substitution, because we are going to put a magnetic field in this lattice. So we have to change the momentum for one momentum that consider also the magnetic field that is encoded in the magnetic potential vector. Of course, they are operators, and then we put the pile substitution in the block energy function, and we promote it to the operator, and we will say that that will be our new Hamiltonian for this system of the electron. So from there, if we propose a two-dimensional wave function, then we will get this equation from here. This arises from the part of the p here in the pile substitution, because e to the I for multiplied by the p operator divided by the h, the Planck constant, we will have a kinetical operator, so we will have a hope in the lattice. So it depends of the orientation of the magnetic field that we are considering. Of course, we are considering a uniform magnetic field, and the potential, the magnetic potential thus will be the Landau potential, which is right there. Don't know if you can see it, the blue part. Well, you take the rotation of that, and you will get the uniform magnetic field. So we are now going to make an ansatz here. That's it, typical an ansatz in a lattice. It has these forms, and then we can rewrite this equation as this. So all the physics will lay now in this matrix. Of course, this is a recursive formula, so we can get the G evaluated in n+1 from the G. So we are talking about the 0 row to the m row. So this is kind of propagated, something like that. Here there will appear this constant that carries the information about the magnetic field, the intensity of the magnetic field in here. And well, this is very important because we want to take it. So yes, what I was saying that you can get the G evaluated in n+1 from the G in 0, and of course this will be a multiplication of matrix step by step. So in order to avoid an exponential growth, we are going to ask to Q to be a when the particle is jumping from one side to other side. That's the only thing that we're going to do. That phase is given by this term in here. This phase will be the same of that phase. Will be the same as that phase. So what happened in the lattice? Our magnetic potential is oriented towards this direction, and it grows as x grows. So if this is the row 0, 1, 2, 3, then the magnetic potential will grow in here. And what happened when one particle circulating in one of these little square of the lattice? Well, we are going to add the phases in here. So let's imagine that we are in the row m plus 1, then the phases acquired by the boson will be 2 pi multiplied by m plus 1 and alpha, something like this. Then it hops to the m row, and this will not acquire a phase in here, and then it jumps toward the right and will acquire a negative phase but multiplied by m, and then return to the m plus 1 row, and that will be the complete circulation of the particles. So the final phase will be just 2 pi alpha. So now the physics is encoded in this. It's okay? So just by the way, experimentally we can do this thing with neutral bosons. We create a square, well, they create a square lattice, and they can add the phases correctly to the bosons when they jump from one side to other. And if we think as that phase as a constant, then we can see that the intensity of the magnetic field that we are simulating is proportional to a to the minus 2, where a is the lattice spacing of the system. So what can we infer about? But this is this is easily explained by if we take a look to the Hamiltonian, because these states where particles are here are energetically most expensive, so the particles tend to not be there because we are close to the alpha equals 0.5, whereas the effect is more remarkable. If we return to the Hamiltonian, then we will have in here, if alpha is 0.5, that we got P multiplied by M. So in this part we will have minus I multiplied by M and P, and in the other side the phase will have the other sign, the plus sign. So we have that one of these will be positive because e to the minus I by multiplied by P will be minus 1, and then it adds energy to the Hamiltonian. So they do not prefer, they prefer to stay in states where M is an even number. It's 0 and 2. Just finally, I'm just going to mention, because of time, the same effect happens when we put a hole in the system. Just the hole is the one that is localized here. For large U, we see that the hole is here and here. Here and here, and the hole is now here and here. So this kind of particle hole symmetry when U is large, and well, the synthetic forces don't see the difference between the hole and the particle. And that will be everything. Thank you.
Gracias. ¿Alguna pregunta o comentario?